Okay, starting off with the Pythagorean theorem, which hopefully is familiar. For any right triangle ABC, a squared plus b squared equals c squared. A and b are going to be the legs of the triangle, and c has to be the hypotenuse. Okay, so the hypotenuse is going to be the longest side. It's also across from the right angle. So in this picture, this would be side C. The other two are A and B. It doesn't really matter which one's A and which one's B. So I'll put them in like that. But it does matter that I'm using lowercase to indicate the sides, A, B, and C. Those are lowercase A, B, and C. If I used uppercase A, it would be for angle A, okay? And angle A is always going to be across from side A. So if angle A is here, side A is here, then angle A is here, okay? And that means my right angle would be angle C, and angle B would be up here across from side B. So that's handy to know, lowercase for sides, uppercase for angles, and then the corresponding sides and angles are always opposite each other, okay? All right, so we've got some special right triangles, the first of which is a 45, 45, 90 triangle. And it's also going to be an isosceles right triangle. All the isosceles right triangles are 45, 45, 90s. Okay. All right. So to solve for the hypotenuse here, we could use the Pythagorean theorem, right? So my A and B would both be x, and then hey, I'll just call this h here. So I'll solve for h here. Okay. So I can say that x squared plus x squared equals h squared. Okay, and then hey, we've got like terms here that we can combine. So x squared plus x squared is 2x squared. Okay, and then I would want to take the square root of both sides of the equation. And then simple radical form, I've got two x's in there, right? I've got twins there. So one of them will get out. So my hypotenuse here is going to be x root 2. Okay, so we can use this. This is kind of a generic triangle because we don't know any of the sides. But if you have the leg in a 45, 45, 90, you just multiply by the square root of 2. Okay, so looking at this next example, we could use the Pythagorean theorem here. Nothing wrong with that. This is going to be 3. Those are both congruent. So you could do a squared plus b squared equals c squared. But just as a nice shortcut, since we're going from a leg to a hypotenuse, I know it's getting bigger, so I'm multiplying, and we're going to multiply by root 2. So this would be 3 root 2. Very handy. So this one's a little different. I have the, this would be x. I have the hypotenuse, but I want the leg. So since it's going to be getting smaller, I'm going to be dividing, right? And instead of multiplying by root 2, I'm going the opposite direction. So I'm going to divide by root 2. So x is going to be 7 divided by root 2, which you could write as a fraction like that. But then I want to put that in simple radical form, and I can't have that radical in the denominator. So since I don't have a twin for the 2, I want to clone one like so. And then I'm going to get 7 root 2 over 2 in simple radical form. And that is reduced, right? You can't reduce the 2's because one's in the radical and one isn't. Okay, we've got our 45, 45, 90s. There's one other type of special right triangle, and that's called a 30, 60, 90 triangle in honor of the measure of the angles. Okay, so let's take a look at this. So a 30, 60, 90 triangle, if I tried to, you can't really get around this with the Pythagorean theorem, say on this problem, because I've only got one of the 3 sides. Same thing over here. So it's really important that you know these relationships. So I've got my hypotenuse over here. And then I've got the 2 legs. Instead of talking about like adjacent legs and opposite legs like we're going to do soon, here I'm going to refer to these 2 legs as the short leg and the long leg. Okay, the short leg is always across from the 30-degree angle, the long leg is across from the 60-degree, and of course the hypotenuse is across from the 90-degree angle. So the short leg is the best piece to have. If you have the short leg, you can just multiply by something to get the hypotenuse, and that something is 2. You can double the short leg. So if my short leg is x, then the hypotenuse would be 2x. Okay? If you have the short leg and you want the long leg, it's getting bigger, so we're multiplying again. Here we're going to multiply by the square root of 3. So if this is x, the long leg would be x root 3. Okay, so let's apply that then to this example. So, hey, short leg to hypotenuse, I'm doubling. So this is going to be 10 because it's 5 doubled. Okay, and then going short leg to long leg, multiply by root 3. So y here would be 5 root 3 then. Okay. Gets a little trickier when you don't have the short leg to start with, like on this next problem. So let's see, this is my hypotenuse, my short leg here, I'll just put SL for short leg, and I'll put LL for long leg. Oops, I accidentally stopped recording there. So sorry for the weird cut. Okay, so if you don't have the short leg, then you want to get it as quickly as you can. So here I have the long leg, so I need to figure out how to get from the long leg to the short leg. Well, if you look back up here, going short leg to long leg, we're multiplying by root 3. So going the opposite direction, we're going to be dividing by root 3. So the way I think of that, first thing is I think, hey, going long leg to short leg, it's any smaller, so I'm going to divide, not multiply. Then you got to remember what to multiply or divide by. But here it's root 3. So in this problem, x, I'm going to take 7 and divide it by the square root of 3. I'm going to write that as a fraction like that. And then I need to put this in simple radical form. So I'll multiply by root 3 over root 3. Then I'll get 7 root 3 on the top. And across the bottom, root 3 times root 3 would be root 9, which is 3. Or you got twin 3's down there if you want to think about it like that. So x here would be 7 root 3 over 3. Okay, and then short leg to hypotenuse, that's getting bigger, so I'm going to be multiplying by 2 here. So I'm doubling 7 root 3 over 3. Sometimes I see people write 7 or 14 root 3 over 6 when they double that, but that's multiplying by 2 over 2. So we're really just doubling the numerator, because think of multiplying by 2 over 1. That's the same thing as doubling it. So this is going to be 14 root 3 over 3, not 14 root 3 over 6. Okay? All right, and that's a 30, 60, 90 triangle. All right, on to the next topic. So let's start looking at some trig ratios. So you may have heard this, this mnemonic device here, this acronym, SOHCAHTOA. So this is a nice way to remember the ratios for sine, cosine, and tangent. Okay. So the h's in here, these two h's are going to stand for the hypotenuse. So I'll just put HYP for hypotenuse. Okay. The o's and the a's are going to stand for opposite legs and adjacent legs. So I'm just going to put OPP, but that's supposed to mean opposite leg. This is adjacent leg. Here's opposite and adjacent again. Okay. And I'll get back to what this actually means in just a second. So let's look at this first example. It says write the a trigonometric ratio for the sine of A. This is a 3-letter abbreviation, but we would say sine even though sin is what it looks like, right? But this means sine. So the sine of A. So A is where you want to think of yourself as being at the triangle, okay? So I want to be at angle A. So look, there I am right there, okay? And then the sine ratio, I'm going to get that right here. So sine ratio is going to be the opposite leg over the adjacent, or sorry, over the hypotenuse. That's the so part of SOHCAHTOA, okay? Opposite over hypotenuse. So my hypotenuse in this triangle is side C. I've got these two legs. These are both legs. One of these legs is across from me right now. That's leg A. So this would be the opposite leg, the one that's on the opposite side of the triangle. The word adjacent means next to, so this leg is next to me. This is next to me too, but it's a hypotenuse, it's not a leg, so this is the adjacent leg. Okay? And yeah, hypotenuse. So opposite over hypotenuse here, opposite is going to be side A, and the hypotenuse is side C. Okay, so that is my trig ratio. A ratio is just a comparison of two numbers. We're going to write these as fractions for trig ratios.
pretty much always. So the cosine of A, then that's right here, the ka part of SOHCAHTOA, adjacent over hypotenuse. So it's all in the spelling of SOHCAHTOA. Whatever comes first goes on top of the fraction. Whatever comes second goes on the bottom. Okay? So adjacent would be B, and hypotenuse is C. So this is going to be B over C. Okay? And then tangent is opposite over adjacent. So opposite would be side A, and adjacent would be side B. And there we go. There's our trig ratios for sine, cosine, and tangent of A. Well, let's see what happens if we're at B. Okay, so if we're at B, the hypotenuse is still the hypotenuse, but the opposite and adjacent switch. Now this leg is the opposite leg, and this one would be the adjacent one, right? So that's going to switch around my trig ratios. So sine opposite over hypotenuse, I'd have B over C. And for cosine adjacent over hypotenuse, adjacent would be A, and hypotenuse is still C. And then opposite over adjacent here would be B over A. Okay? And you're usually going to be at the acute angles for SOHCAHTOA. Tangent isn't even going to work from the 90-degree angles. But yeah, almost always we're going to be at those acute angles. Okay? Okay, so now let's look at why this is useful. What can we use these trig ratios for? Well, we can use them on a problem like this next one. So looking at this, I can't solve for x with the Pythagorean theorem because I've only got one of the three sides. It's also not a special right triangle, so I'm kind of stuck in both those approaches. But I can use SOHCAHTOA. So what you want to do is put yourself at one of the acute angles. You want to be at the one that is marked. So I want to be at the 34-degree angle. So I'm thinking to myself, there I am, okay? And then I'm looking at the sides of the triangle and thinking, what am I dealing with here? Well, the hypotenuse is unmarked. This would be the opposite leg, and this would be the adjacent leg. So I'm dealing with the opposite and the adjacent. And that's where SOHCAHTOA comes in. Now I want to think, okay, I'm going to use one of these three parts, and I want to look for the part that uses opposite and adjacent. That would be tangent, right? So I can write a tangent ratio. So I'll write TAN for tangent. I want to say where I am. I'm at the 34-degree angle. I don't know the name of the angle, but even better than that, I know what the measure is. So I'm at the 34-degree angle. And opposite over adjacent, so opposite would be 8. That's going to go in the numerator. X is adjacent, so that goes down here, okay? And now I'm going to isolate x first off, okay? So one way to do this is to multiply both sides by x to clear the fractions, and then divide by the tangent of 34 degrees. What's going to end up happening if you do both of those things, these are going to switch positions. So I like to do a little maneuver called the incredible switch. So whenever we've got the situation, we can switch the position of those two things. You can't do it with the numerator, so it really only helps when the x is in the denominator. But here, this is where we're going to end up algebraically if you multiply by x and then divide by the tangent of 34. That'll get us there, okay? Now the tangent of 34 degrees is a number. I don't know what that number is personally, but my calculator does. So what that refers to is that any right triangle with a 34-degree angle here is going to have the same ratio of these two sides. So it might be, they're going to be similar triangles. They might be bigger or smaller, but they'd have the same shape and size, which means that ratio is going to be the same. You know, so if this was 8 and let's say this comes out to 4, well, then it'd be the same angle if I had 80 and 40, right? Because it'd be the same ratio. I'm not saying that this is going to be 4. So what I want to do then is go to my calculator. You want to make sure you're in degree mode on your calculator. So on these calculators, mode buttons right there, I'm in degree mode. That's the third one down. You do not want to be in radian mode because this angle is measured in degrees. There's also, you can measure angles in radians, which we haven't gotten to yet, but we will later. Okay. So I can type in the tangent of 34 degrees and hit enter, and that's about 0.6745, something like that. Okay, so I could do 8 divided by that decimal, and that's fine, but if you do that, you want to use as much of that don't round this to 0.7. You'll get a pretty lousy answer if you round that to 0.7. So try not to round too much as you go. So you can just start typing in the whole decimal. You know, the more of that you use, the better. Another thing you can do on these calculators is hit second and then the little negative button down here, because it says ANS above that. So that means my last answer. Then it repopulates that last whole long decimal without me actually having to type it in. So that will work, 8 divided by that decimal. Or on these calculators, I can just type this in as 8 over the tangent of 34 degrees, all like that. If you have a simpler calculator, you might need to do it in steps. But try to avoid rounding as you go. I usually round my answers to the nearest hundredth at the end of the problem. But if you round as you go, it'll throw your answer off the more you round, okay? All right, so let's try another here. So here I've got the tangent of, I've got a 23-degree angle. I haven't looked at if it's tangent yet. I want to be at the 23-degree angle. Here I'm dealing with the opposite and the hypotenuse. So this one's not going to be tangent. I'm thinking of SOHCAHTOA again, and this would be the SO part of SOHCAHTOA, right? So I'm going to use sine here. I have to use sine. So sine of 23 degrees is going to equal opposite, which is 7, over x. Okay. So again, I'm going to do incredible switch here. That's a maneuver I invented, I think. At least I invented the name for it. Okay. So I'm pretty proud of that. All right, 7 over the sine of 23 degrees, and I've got about 17.92. I'm going to the nearest hundredth. Okay. All right. So let's try a word problem. So Ed is flying a kite on a 100-foot string. Let's draw a picture. All right, here's Ed. And here's the kite on a string. The string is 100 feet. Okay. And then it says the angle of elevation from Ed to the kite is 32 degrees. So if you think about Ed looking up towards the kite, you would have to look up at a 32-degree angle, okay? And then we're asked for the height of the kite. That would go right there. And now this is just a SOHCAHTOA problem, okay? This didn't talk about Ed holding the kite 4 feet above the ground or whatever. Sometimes you'll get that, and then you get the whole triangle floating above the ground, which means you'd have to add 4 to your final answer. But here, let's just pretend the kite is tied to the ground. Also, we have to assume the ground is flat, or these won't work. We wouldn't have a right triangle then. But we do have a right triangle here. So from the 32 degrees, we're dealing with opposite and hypotenuse. So this is going to be sine again, just like the previous example. So the sine of 32 degrees is going to equal x over 100, opposite over hypotenuse. Incredible switch doesn't do me any good here, because you can only switch with the denominator. But all I need to do to isolate the x is multiply both sides by 100. One mistake I see is sometimes people will multiply by 100 here, and then they'll write this as sine of 3200 degrees. Well, you can't just multiply the 32 by 100. You have to multiply this decimal by 100. Okay? So put the 100 out in front of the sign, and then it'll be clear. It's kind of a coefficient, because the 32 isn't a number in itself. It's just the contents of the sine function, and it's the sine of 32 degrees, which is something different, okay? So some calculators might have to put this in your calculator first, then multiply by 100. If you've got a calculator like mine, you can just type it in, 100 sine 32 degrees, and that puts us at 52.99. And if we're going to the nearest hundredth again, 52.99, and this is in feet. And there we go. Okay.